Hi, in this video, I'd like to talk about some optimizations that we can do for linear and quadratic probing. To do that, let's quickly review a scenario that we discussed before, and that is if we have this hash table and now we want to insert the number 14, then when we get to this bucket that has a deleted 7, the question then was, can we reuse this deleted bucket to hold the new data 14? The answer was that we cannot, because if we put in the number 14 here and then we stop the probing because we are done inserting 14, then we can end up with having duplicate 14 in the hash table because there was another 14 that's later in the probing sequence. Now let's consider a slightly different scenario in which we try to insert the number 7. So when we get to this bucket that has been marked deleted, but it has the number 7 in it, which matches the one we are trying to insert right now. So can we reuse this bucket to hold the same data? So let's go ahead and just put the 7 back in this bucket, make it active again, and stop the probing sequence. We take a look at the rest of the hash table. Everything looks fine. There is not another 7 in the hash table, so we didn't have any duplicate data, as was the problem with inserting 14 that we saw a little earlier. So the rule, as it turns out, is that during insertion, we can use a deleted bucket to store the new item, but only if the item that's already in the bucket equals to the new item that we're trying to insert. So by following this rule, we'll guarantee that an item is always unique in the hash table. There's never duplicates. Now, several comments regarding this particular techniques. It is an optimization because it doesn't really change the correctness of the hash table implementation, right? Whether we have this or not, in both cases, the hash table is still going to function correctly. But using this technique, it will make a certain case faster. And what that certain case, it is a very specific case, right? It is if we remove an item and then if we reinsert the same item at a later time, then yes, we can put it back into the same bucket if that bucket is still there. And then finally, this particular optimization is actually independent of whether we're using linear probing or quadratic probing. There's nothing in this optimization that dictates how we do the probing. It only concerns the state of the bucket and the relationship of the item in the bucket to the item that is being inserted. And as we'll see, doing this in insertion actually allow us to make some additional optimizations in a couple other operations. But first, I'd like to ask you to implement this optimization in the hashqp insert method and make sure it passes all the existing tests. So please pause the video and give this a try. So what we have to modify was this condition that the bucket is available for insertion if it's empty, that was there before, but also if it is a deleted bucket and the item in the bucket equals to the one that is being inserted. Another slightly trickier modification is that we increment the number of occupied bucket only if we are transitioning from an empty bucket to an active bucket, right? If the bucket was deleted, that the count for the number of occupied bucket has already been previously incremented, so we didn't have to do that again. So now that we can guarantee each item in the hash table is unique, we can discuss some optimizations in other operations, such as contains, the membership check. So previously, during the probing sequence, we can only stop when we run into an empty bucket. But now if we actually find the key that we are looking for in a bucket, but that item has been deleted, we'll also know that that item can never be anywhere else in the hash table. So we can also stop and return the item is not found in this case. And lastly, I would like you to think about if we can apply the same optimization in the remove method, and just go ahead and give it a try, make the modification, and see if it passes all the tests. And it should, assuming you've done the optimizations correctly. So this concludes the video on probing optimizations.